Okay, so now we're on to part 5, and we're going to talk a bit more about things that you can do to try and boost power in your study design. One of the things that I listed there was just optimizing your experimental design. This is a really massive topic. I mean, most of us may differ for you, but most of people, I think, don't get formally taught about experimental design, which is a really important topic if you want to be a researcher. I can recommend this book by Stanley Lazick. Although it says experimental design for laboratory biologists, a lot of the points he makes are relevant for broader disciplines, although the examples he gives are mostly for animal studies and pharmaceutical type studies. But he covers a lot about problems with reproducibility in research and has a lot of examples in R of things you can do. I'm going to be fairly simple today and just illustrate how design can make a big difference by simulating some numbers and then showing you how the results vary depending on whether you're using a within subjects or a between subjects design. And I'll also take the opportunity to introduce you to a package called Faux by Lisa de Bruin, which is designed to simulate data and goes up to much more complex designs with lots of examples of how you can apply it. I just want to say a bit, though, about study design, because if you want to pre-register a study, you'll often be asked, well, what sort of study is it? And you find that, I mean, I myself have found I have to think, what sort of study is it? Because you have just sort of thought, oh, I'll do this study without really thinking through the logic of what you're doing. Are you systematic manipulating a variable to see its effect? That's an experiment. In my field, people often talk about things being experiments that are not really experiments, because you might be, for example, comparing two clinical groups. You haven't manipulated anything. You're just taking what's there naturally in terms of the clinical groups. And so that's really more of an observational study. So that distinction can become quite important, because in an observational study, you don't have experimental control in the way you do in an experimental study, and that can affect your design. If you are then taking it a step further, if you're doing an experimental study, are you comparing different groups, two or more groups? Are you obtaining repeated measures on the same individuals? Have you got a mixed design with two or more groups with repeated measures? So you've got both. And Lazick covers the cases where you have another level of description, such as with animals, you may be applying manipulations to litters or to clusters of cells. So the unit of experimental analysis can vary depending on your discipline. And it's important, as Lazick emphasizes, to know what the unit of analysis is when you do your studies. But I won't go into that here. That's a bit beyond the scope of what I'm covering. If you're doing observational studies, quite often they're correlational. Regression analysis is really just an alternative approach to that. You may be doing some sort of group comparison from observation from naturally occurring groups, or you may be looking at longitudinal data. So there's a repeated measures element to that. If you want to design a good study, the basic goal is to minimize or control unwanted sources of variation and maximize the effect you want to evaluate. And when you're thinking about unwanted variation, it could be random noise or it could be systematic bias, both of which are undesirable. Random noise provides threats to validity because it just adds slop, noise to your observations, and these can obscure the effects of interest. If you've got human or animal participants, heterogeneity can often be a problem if you're doing between group experimental designs. On the other hand, if you're looking, for example, at correlates of particular, if you're interested in individual differences and things that correlate with those, you actually may want wide variation in your group rather than having a very restricted range. So you can't say heterogeneity is always bad or always good. It also depends on who you want to generalize to. But essentially, you have to think through what you're doing and not just go with what everybody's done before. And of course, then you can have participants in variable states. You may want to exclude people who've been drinking or having too much coffee. It depends what you're measuring. You may or not be able to do that, but it's the sort of thing to think about whether people are temporarily under the influence of something that may have, or they're just very tired, may have had no sleep, under the influence of something that may affect their performance. And then in your measures, there may be just random fluctuations, which may be to do with things about your subjects who may have poor attention. This may be a general problem if your tasks aren't very interesting. You may have collected too short a sample of behavior, and I'm going to come on to talk about how that can affect your statistical power. And your task design needs to be thought about carefully. I mean, if you're using questionnaires, what's the length of the questionnaire, how's it worded, what are the response options? All of these things can damage the validity of your studies and introduce unwanted noise. In this case, even systematic bias, if, for example, people systematically misunderstand something. We need to have measures generally that are reliable and not subject to random fluctuations from time to time, unless you happen to be studying random fluctuations. I mean, you may be interested in how people fluctuate over time. But for many settings, this is an issue which isn't adequately thought about. People may get very consistent measures, but they're not measuring what they thought they wanted to measure. That's the situation depicted on the left, where you've got a measure that's actually got some sort of systematic bias. Very commonly, people just have measures that are just not very well constructed, so they're not particularly good representation of what it is you're trying to measure, but also then they change from one occasion to the next. So what you want is something that's both valid, in the sense it's measuring what you want, and reliable. And there's another exercise later on reliability to show you how important that is. I'll say a little bit about systematic bias, although we're not going to be simulating that in this course, but just to bear in mind that systematic biases will introduce confounds in your study, and so make it difficult to understand what's going on. There may be order effects, so if somebody's getting better and better at doing the task as they go through, and you've got that confounded with some manipulation, you need to control for that, typically by counterbalancing. There may be item effects, such that some items are easier or harder. You can explicitly analyze those or allow for them with some designs, and also you may want to counterbalance. There's a thing that's ascertainment bias, which means that your sample is not representative of the group that you're trying to generalize to, and it's often overlooked. People will just take convenient samples without realizing that they're missing quite a lot of the population. You should avoid that as far as is possible, but it's not always possible. But if you have dropouts, people sometimes just don't analyze the dropouts. It's actually quite important to take into account dropouts in your analysis. And then another sort of bias is experimenter effects, where the experimenters really often unwittingly is biasing the data they collect, perhaps in the direction of getting an effect of interest. That's a big area of research in psychology, and the more you can automate your procedures or blind allocation to groups, or ensure you use random allocation to groups, the better. But I want to start just with a little demonstration demonstrating this package called Faux, which will demonstrate how your design can affect your power, and we'll work through this script in small chunks to work out what it does. I'll move to R in order to show you the script. So you should have downloaded this one, which is called Faux Demo BW. That's between and within. And it's just going to compare the same data analyzed in a paired or an unpaired t-test. This package is really useful for simulating much more complicated designs, but this is just a little easy introduction to it. So we'll start with require faux. So you should have I actually got faux? Got a lot of warning messages. Yes, sometimes you get these with certain variations of R, that you get strange warning messages that turn out not to be terribly important. So you specify what is your within subjects factor. You give it a label. It's got 2 levels, morning and noon. I've pared down an example which I think had 3 levels, had evening as well or something. And you're also going to specify your means. So these are the means for morning and noon. One is 10 and one is 12, whatever these are, memory test scores or whatever. And then this is a part of the Faux package, this sim design. So you're basically saying, you're creating a little data frame, which we can then look at. 20 observations of 3 variables. So it's got a subject ID, and then it's got a score for morning and a score for noon. And these are generated just very similarly to the using R's basic routines for generating random numbers. So we've got that simple little design, and we can do a t-test on it within subjects, which means you're comparing each person's morning and noon scores to each other. And we see the result down here. So we get a t-value of 3.51, and the mean of the difference is 3.143. And then you can do a between subjects, which is the sort of t-test you'd normally do if you didn't have repeated measures, but you had 2 groups of people. But you can apply that sort of t-test to this data set. And again, notice that the difference up here between the 2 groups is 3.14. It's still 3.14. That's the difference of the mean of X and the mean of Y. But the t-value is now lower, and the p-value is also smaller. So we've got exactly the same data, but the way we've set up our analysis influences what we get. Now, why are the results so different? The answer is that the within subject analysis tests whether the difference between the means differs from 0. So we can compute that difference and look at it. Doesn't seem to like that. So let me just make sure I've got, not sure why it's saying, let's see if that will work. Yeah, okay, not sure why that's not working. Let's just make sure we've got that. We've got the different scores here. So this is the difference for each subject between morning and noon. And we're just trying to plot a histogram of those, which it seems reluctant. It seems to want me to call plot new, so I can do that. I'm not sure quite why it wants that, but let's see if that helps. It seemed to be in a funny mood and need plot new, which it doesn't normally need, but I must have set something else. So you can see that this histogram of the different scores, what the within subjects t-test is doing is comparing those values to 0, saying that there's no difference between the 2 conditions. And you can see that most of them are bunched here over to the right, and that indeed turns out to be a significant difference. But if you treat the 2 measures as if they come from different groups, as you're doing in a between subjects analysis, then you are actually comparing, let me just show you this, you're comparing this set of numbers, their mean and standard deviation, with this set of numbers and their mean and standard deviation. And as you can see, there's a lot of variability from one subject to the next, and that enters into the analysis. If you're doing the within subjects, it doesn't enter into the analysis because you are only interested in the difference. And so the fact that this is a difference of 2 with the person starting with 14 and going to 16, and then here's a difference of 2, which is going from 5 to 8. Those are treated as the same. It's not taking into account the variation in the base data. It's just taking into account the difference. And that gives you a more powerful test because you've got rid of the variation that is down to subject variation. So that is just part of the Faux package to plot the morning and noon distributions. And this is just what is being compared in the t-test between groups. You get confused with this, these 2 distributions. rather than the different scores for individuals. So given that's the case, you have to think, how could you modify this design to generate data that would give similar results in a paired versus unpaired t-test? And I've put here a hint: try varying the value of R in line 21. So R is specifying the correlation between the two variables. So these are coming from the same person, and so they tend to be correlated. And we've specified how highly correlated they actually are, because somebody is not going to suddenly jump around and change their score massively from one occasion to the next. So that is the clue that you need to see if you change that R, you should find that that has a dramatic effect on the results. Now, if we want to, I'll put that on hold and park that idea, and you can play with that. But let's just now try and plot the p-values from the two types of, I'll just make the screen a bit bigger, two types of method. Just going to think about it a bit. When it's down here, just like that, it's just thinking. You can see on the console, it hasn't got its little triangle, so it's processing. And there it goes. And what you can see is that you've more or less doubled the power, not quite doubled. This is 0.399 between subjects. Within subjects, it's 0.686. So it makes a massive difference to your power, whether you use the within or between subjects with these particular settings of the parameters. Okay, let's go back into PowerPoint and just, I'll say that's something for you to definitely try out on your own a bit more. And if you have questions that come up, we can deal with them in that interactive session. I'll just draw your attention, for those of you who want to use much more complicated designs, Lisa De Bruyn, who made the Faux package with Dale Barr, has also got a paper in SciArchive on using mixed effects models. And this is all built on the same basic idea that you can start simulating designs where you might have variation in items and subjects, and you're putting them through a mixed effect model. And the point is, it doesn't just give you some idea about power, but it helps you understand how those models work and how they differ from more simple things like analysis of variance. SimStudy, which I introduced you to with an earlier simulation, here's a website that tells you a bit more about using that and how you can generate data with many predictors. So that's useful. And this is one of my favorite packages, but one of the most complicated, is a Declare Design, which is developed by political scientists for analyzing, mainly using using a variety of different designs used in political and social sciences. But the nice thing about this is it's a package that simulates data and then gives you not just power analysis, but it allows you to evaluate things like whether there's bias in your estimates as well. But it isn't, they adopt a formal model of experimental design, and they're in the moment producing a book that explains this stuff. But it's really, I couldn't understand this when I first came across it, and I tried to write a very simple little script to give you the sort of basics of it, and the authors of this were very helpful in doing that with me. And I have to say, it's a very appealing approach, because it's really for nerds. It's a more sort of formalized approach to experimental design, and allowing you to compare different designs and see how useful they're going to be. But I'm a novice in that, I have to say. So have a play with that script, and then if you come across issues or things that might affect your own research or things you don't understand, keep a note of them, and then we can discuss them in our session that we have interactively.